This module covers flying and handling qualities. We obviously know that performance in terms of speed, range, and endurance is what sells airplanes. But how do we know if our airplane is well designed? And what does that mean? Well, we want it to be safe to fly in its mission area, also effective and preferably easy to fly in its mission area. That's why we need flying and handling quality standards to evaluate the airplane design. So let's come up with specific definitions for flying and handling qualities. Flying qualities, which will be abbreviated FQ, is the stability and control characteristics that have an important bearing on the safety of flight and on the pilot's impressions of the ease of flying the air vehicle in steady flight and in maneuvers. For handling qualities, which we often use HQ for an abbreviation, it's those qualities or characteristics of an air vehicle that govern the ease and precision with which a pilot is able to perform the tasks required in support of the air vehicle's role. Another definition that we'll use but we'll treat as a separate topic is called PIO, or pilot in the loop oscillation. And that's an unintentional, sustained, or uncontrollable oscillation that results from the efforts of the pilot to control the aircraft. Handling qualities is often considered to be a subset of flying qualities. But we also want to distinguish flying qualities from handling qualities. And so we use open and closed loop as a means of distinction. So for stability and control, we're going to get those answers using open loop interaction with the pilot. But for handling qualities, we're going to use a closed loop task to assess those. So open loop systems, it just means that the inputs to the system do not depend on the output. Again, we're going to look at aircraft stability for an assessment. And at the bottom you can see samples of open loop inputs. In other words, the pilot could do this, or the computer could do this, independent of what the air vehicle output is. They just focus on putting in the input. So it could be a doublet, a singlet, or a step input, but again, there's no feedback required for the pilot to track something. Contrast this to a closed loop task. Here is a fighter aircraft that's doing some air-to-air tracking, but basically the pilot performs tasks that require them to make inputs based on the output of the system. Other examples could be crosswind landings or just following a glide path. And so we see here the pilot now becomes an integral part of the control loop and is relying on the feedback of the system to impact the pilot's inputs to perform the task required. So when we think of aircraft design and test, it is an iterative loop. So we have the design engineer methods, which involve equations of motion and math techniques. And that's going to give us basically an analytic and simulator result, or a model of the aircraft. We then go ahead and make the design and prototype. Once we have a prototype, we begin to do flight test. We have various flight test techniques. Open loop tasks that will give us data that we'll compare to aircraft specifications, and closed loop tasks where we'll have pilot ratings and comments and a qualitative analysis. But ultimately we'll take data from both of those in a report and feed that back to the aircraft designers for improvement. So where are flying and handling qualities defined? For civil and commercial aviation, it's in the FAA, or if you're in Europe, it would be EASA. For the FAA, it's Part 23 and Part 25. And for those regulatory documents, There's also associated advisory circulars. For Part 23, that circular is 23-8 Charlie. And for Part 25 aircraft, that circular is 25-7 Charlie. And EASA has similar numbering schemes as the FAA. They use CS-23 for light aircraft and then CS-25 for larger aircraft. In the military, at least in the United States military for Air Force, Navy, and Marine Corps aircraft, the guiding document is MIL Standard 1797. Again, the FAA follows the Code of Federal Regulations. Title 14 covers aeronautics and space, and as you can see in the bottom in the red box, Part 23 covers the airworthiness standards for normal utility, aerobatic, and commuter category airplanes, and Part 25 is airworthiness standards for transport category airplanes. Here's the two advisory circulars that dictate how an airplane, in terms of a method of compliance, will be certified. And there's one for Part 23, that's 23-8 Charlie, and there's one for Part 25, and that one's 25-7 Charlie. So we'll do a brief history of the flying quality standards. In January 1908, we knew that there was a statement that, quote, "It should be sufficiently simple in its construction to permit an intelligent man to become proficient in its use in a reasonable length of time." As far as the history for military standards, we see in the 1940s, during the World War II era, is when standards began rolling out, and 1815 was the main one. And then in the late 1950s, 60s, and 80s, which is often considered the golden age of air vehicle development and flight test, MIL F 8785 was the dominating standard. In 1987, that standard was replaced by MIL Standard 1797, which became a handbook in 1997, but then back to a standard in 2006. For stall, spin, departure, it's MIL S 83691. So throughout the history, we know that many authors, many groups were involved, many decades of experience, and with that becomes some issues of lots of objectives, sacred cows. And so the MIL standards are easy to misuse without a roadmap. A table of contents is not enough. Many people speak the language of the version they use the most, not always the current one. So if you did most of your design in the 80s and 90s, you may use an earlier version of the standard than the one that's used today. The most comprehensive flying qualities standard is MIL Standard 1797. And we'll spend the majority of this module on the military standard. So we've introduced the FAA standards, but this is where the real details for flying qualities is defined, because the military have all kinds of aircraft, and we'll talk about all the different aircraft, the different categories and phases and levels of aircraft and performance that we need to define to really dive into the flying qualities topic. With respect to flying qualities, one size doesn't narrowly fit all. And so the first definition we have to work on is the actual aircraft classification. So the MIL standard defines 6 classes of aircraft, and we'll go through these one by one. Class 1 are small light air vehicles, such as light utility, primary trainer, and light observation. So you can think of a Cessna 172 for Class 1. Class 2 would be medium weight, low to medium maneuverability air vehicles, such as heavy utility search and rescue, light or medium transport cargo tanker, early warning, electronic countermeasures, airborne command control or communications relay, anti-submarine, assault transport, reconnaissance, tactical bomber, heavy aircraft, or trainer for Class 2. Class 2 also sometimes is designated with another symbol, a -C for carrier-based or -L for land-based. So you can think of a Class 2 medium-weight aircraft as maybe a C-130. Class 3 is large, heavy, low to medium maneuverability air vehicles, such as heavy transport, cargo tanker, heavy bomber, patrol early warning, electronic countermeasures, airborne command and control and communications relay, or any trainer for Class 3 aircraft. So this is where large transport aircraft, think of Airbus A380, 747, basic airliners would be Class 3 aircraft. The next class is 4, which is high maneuverability air vehicles such as fighter, interceptor, attack, tactical reconnaissance, observation, or any trainer for Class 4. So this is where F-22, F-35, F-16, any kind of fighter aircraft, F-18 for the Navy, would fall under Class 4. Class 5 are rotorcraft, and Class 6 are vertical or short takeoff and landing air vehicles. Within a specific class of aircraft, we can't expect flying qualities to be one size fits all for every flight phase category. So we're going to further break down definitions for flight phases. Category A are those non-terminal flight phases that require rapid maneuvering, precision tracking, or precise flight path control. Category B are non-terminal flight phases that require gradual maneuvering without precision tracking. And Category C are terminal flight phases that require gradual maneuvering with accurate flight path control. On the right-hand side of the chart, you can see various definitions or examples of each flight phase category. For example, A could be air-to-air combat, ground attack, weapons delivery, aerial recovery, reconnaissance, in-flight refueling, terrain following, anti-submarine search, close formation flying. Category B, climb, cruise, loiter, in-flight refuel, descent, emergency descent, aerial delivery, etc. And Category C would be takeoff, catapult takeoff, approach, wave off, go around, and landing. So the terminal phases of flight. Now that we have the class and category of flight defined, we need to define what a level of suitability is. And we typically consider 3 levels. Level 1 would be satisfactory. It means the flying quality is clearly adequate for the mission flight phase. Desired performance is achievable with no more than minimal pilot compensation. That's the level 1, which is what we want. Level 2 is what we would consider just acceptable. The flying quality is adequate to accomplish the mission flight phase, but some increase in pilot workload or degradation in mission effectiveness, or both, exists. And the third level is controllable. Flying quality such that the air vehicle can be controlled in the context of the mission flight phase, even though pilot workload is excessive or mission effectiveness is inadequate, or both. The pilot can transition from Category A flight phase tasks to Category B or C flight phases, and Category B and C flight phase tasks can be completed. There's another definition without a level associated with it, and that is just recoverable. Flying quality is such that control can be regained following loss of control due to departure, failures, or atmospheric disturbances. Next, we'll walk through the different MIL Standard 1797 sections and just kind of put some general words to what we're seeing in the paragraph structure. In Section 4 is where aircraft classification, flight phase categories, and flight envelopes are defined. Section 5 brings in some of our handling qualities maneuvers, and we'll talk about the Cooper-Harper Rating later in the module. It also includes stall and high angle of attack indications. Section 5 specifically calls out some of the modes we've discussed so far, which include phugoid, short period. Also looks at flight path considerations and longitudinal control power. Section 5 also contains guidance on stick force per G and longitudinal stick feel requirements. And the graph at the bottom right shows you an indication of how you would define, say, stick force per G. Section 5 also brings in the lateral directional modes we've talked about, roll mode, Dutch roll, spiral, even yaw time delay, so lateral directional with associated frequencies and damping. It talks about roll linearity, and then there's some special things for fighter aircraft. Also lateral stick feel requirements. Section 5 deals with steady side slips, crosswind requirements, and cross-axial control harmony. And finally, Section 5 brings in high angle of attack and stall testing, maximum control limits, and the ability to trim the aircraft. And ironically, Section 6 covers the intended use, or the mission, which I would think would be first in the document, but here it turns out in Section 6. So now we'll walk through the 5 classical modes of motion and then look at what the MIL standard defines for minimum or maximum values for each parameter. We'll start with the short period and phugoid modes, and as you recall from previous modules, the general fourth order transfer function of elevator deflection to pitch angle is shown. And we know that that denominator factors into 2 second order conjugate pairs, and one's the phugoid mode and one's the short period mode. So assuming we know all the values of the transfer function, we can then see what the specifications are or standards are for flying qualities depending on the flight phase category. And you can see here with the transfer function, if we know the damping ratio of the short period mode, we can see that it's specified for the 3 categories of flight, and also what's considered level 1, desired performance, level 2, adequate, or level 3, which is the worst. So we really want an aircraft with level 1. So you would take the damping ratio, and right there it would show you the minimum and maximum values. Likewise, you would take the natural frequency of the short period mode, and you would also look at category A, B, C, and level 1, 2, and 3 requirements on minimum values for the natural frequency. The time constant T theta 2 is also specified. You may wonder what CAP stands for. CAP is control anticipation parameter. It's the ratio of initial pitch acceleration to the final normal acceleration. Basically, you can think of it as how pulling the stick will change flight path angle. And so CAP has a couple definitions there in terms of the frequencies, the normal load factor, and angle of attack. But we can also substitute velocity, L alpha, and other things to get this basic definition here, which involves the frequency, speed, G, and our time constant T theta 2. So once you calculate this CAP value, there are also specifications for ranges of acceptable CAP for the various flight phase categories and level 1 and level 2. For the phugoid mode, a little bit simpler to digest the flying qualities requirements in terms of just the damping ratio or the time to double amplitude. We know that the phugoid mode can sometimes be unstable, so there could be a time to double. But assuming it's stable, we know that level 1, the phugoid damping ratio should be above 0.04. For level 2, just needs to be anything positive. And we can get damping ratio from the transfer function by looking at the value in the denominator with the red circle. So knowing these values in the MIL standard, we can start looking at longitudinal design. So extensive research was done to develop these guidelines relating the levels of flying qualities with flight dynamic characteristics. So this enables us to account for desired flying qualities early in the design phase. So again, you can see the graph on the lower left where you can look at how frequencies and damping ratios play off each other, and there's obviously a sweet spot that you would want for satisfactory in your design. And we know that, at least in terms of damping ratio, we covered on the previous 2 slides. Here's kind of just a top level look at for the phugoid and short period mode for what kind of damping ratios you really want to target. If we use just even the approximated short period dynamic equations, we get values for the frequency and the damping ratios, and so we can basically look at flying quality standards as the primary driver for selection of static longitudinal stability and pitch damping. And these are values that drive the design for the horizontal tail, the main wing, and the fuselage. We'll now move into the 3 lateral directional modes of motion. And just recall there was the Dutch roll, the roll, and the spiral mode. In the case of Dutch roll, we're going to see that it's constrained in minimum frequency and damping. The spiral mode will be constrained in minimum time to double amplitude for the unstable mode. And for our roll mode, it'll be constrained in maximum time constant. We'll walk through each of these one by one. Here's the requirements for Dutch roll mode. You can see we have breakdowns in terms of what's level 1, 2, and 3. We also are going to have breakdowns into category A, B, and C flight, and then different classes of aircraft, 1, 2, 3, and 4, whether it's land or carrier based, etc. And so you can see here, again, that there will be a minimum damping ratio defined and also a minimum frequency. And so, as well as the multiplication of damping ratio times frequency. So these are the targets that you would want for a level 1, 2, or 3 aircraft. And again, level 1 is the goal. Depending on whether you're class 1, 2, 3, or 4, what category of flight would dictate what your minimum Dutch roll frequency and damping ratios should be. For spiral stability, we're really only concerned that if it's an unstable spiral mode, that it's got a minimum time to double amplitude. So in the case of category A and C flight, for level 1, we would want that to be 12 seconds, would be the minimum time to double. Anything quicker than that, the pilot may not be able to recognize it and make a compensation input in time to address it. So that's why we define a minimum time. For category B flight, 20 seconds. Again, our goal is level 1 aircraft. So those are the 2 numbers that are most relevant for the design phase. In the case of the roll mode, the maximum roll mode time constant is what's specified. We want the roll mode to be relatively fast, and so that's why we're going to specify the maximum time constant. Now you can see here for category A, class 1 and 4, so light aircraft or fighter aircraft, you want it to be a quick roll rate, but they don't expect a Class 2 or 3 aircraft, like medium to large transport aircraft, to have as fast of a roll rate. So you see that the maximum time constant is allowed to get bigger for those class of aircraft, 1.4 for level 1, 3.0 for level 2. But for fighter aircraft and small aircraft like Cessna, you want that thing to roll pretty quick, so that's why for level 1 it's specified to be 1.0 and 1.4 for level 2. So here's an example where we actually see a performance requirement specified in a flying quality standard. In the case for roll performance, we can see that Class 1 aircraft, so your light trainers like a Cessna 172, should be able to change their roll angle by 60 degrees. And there's the specifications for level 1, 2, and 3 as far as time for a 60-degree roll change. A Class 2 aircraft, which is like a C-130, so a medium-sized aircraft, you would not expect that airplane to be in a 60-degree bank turn. So in this case, for Class 2, they're going to specify 45-degree time to roll through the 45-degree angle change. So again, you can see how it depends on the class of aircraft to what you would want to specify in terms of roll performance. Now, to get the roll performance, this is where we bring back the qualitative feel or the flying qualities aspect. So this is a maximum control force that was required to get the desired roll performance. And again, you can see here, it depends on whether it's a center stick or an actual wheel or control yoke that you could put two hands on. So you're allowed to have more force required if it's two-handed operation versus a one-handed center stick. And so the maximum forces are specified there. But also you don't want the controls to be so light that you can make the airplane roll so quick that it would be unsafe. So there's also a minimum roll force specified that for level 1 would be 1/4 the values listed in the table. For level 2, 1/8 the values listed in the table. So there's a maximum force specified as well as a minimum force specified. And we could see that some of these forces were based on studies that were designed in the 1980s from this technical report here, where it looked at men and women and what percentile population as far as size of the human. So fifth would be a relatively short person, and 95th percentile would be the highest or tallest person in that range. And you can see what the stick force deflections that were achieved, whether it was stick left or stick right. The FAA actually specifies maximum control forces higher than what the military specified. And so the FAA has contracted Florida Tech to help them research that. They've done studies as well because they recognize that these forces do seem quite high. And in a study published in 2019, they found that only 68% of the sample representative of the current pilot population could meet these values listed in the table. So we expect our advice to the FAA, and we expect future guidance that these values will come down as far as the maximum forces allowed during flying qualities types of applications. Next, we'll focus on handling qualities. And again, that definition is those qualities or characteristics of an air vehicle that govern the ease and precision with which a pilot is able to perform the tasks required in support of the air vehicle's role. Again, we looked at handling qualities are closed-loop tasks. The pilot performs the tasks required to make inputs based on the outputs of the system. And we used examples like crosswind landings, following a glide path, or air-to-air tracking. And we know that the basic airplane model and all its stuff is sitting right here, but closed loop means we're going to add the pilot, and the pilot is going to use the feedback signal to affect their future inputs. So that's what closed loop control and handling qualities is all about. Again, here's the air-to-air tracking example. So let's walk from the aircraft role to the pilot workload and see how that relation progresses. The role is the function or purpose that defines the primary use of an aircraft. The mission, the composite of pilot vehicle functions, must be performed to fulfill operational requirements. May be specified for a role, a complete flight, a flight phase, or a flight subphase. Task is the actual work assigned a pilot to be performed in completion of or as representative of a designated flight segment. Performance is the precision of control with respect to aircraft movement that a pilot is able to achieve in performing a task. Compensation is the measure of additional pilot effort and attention required to maintain a given level of performance in the face of deficient vehicle characteristics. And finally, workload is the integrated physical and mental effort required to perform a specified pilot task. So now let's think about rating the aircraft handling qualities. We know that handling qualities form the relationship between the stability control characteristics of the aircraft and the perception and motor skills of the pilot. So you can imagine this relationship is a bit hard to quantify, right? So what is the range of values of short period frequency and damping ratios such that the aircraft is easy to fly for the average pilot? We use a quantification approach based on the pilot's opinion to help determine the handling qualities. And so some rating scale is in order, and the widely accepted version is called the Cooper-Harper Rating scale. So the Cooper-Harper scale was defined in NASA Tech Note D5153 from 1969, entitled The Use of Pilot Rating in the Evaluation of Aircraft Handling Qualities by George Cooper and Robert Harper. So here is the Cooper-Harper Rating scale. It involves the pilot going through a series of questions, yes or no, and ultimately arriving at some pilot rating numerical value. Though the numbers are used, it's considered an ordinal scale, not a numeric scale, and so one shouldn't look at the relative difference between, say, a 2 and a 4, where a 4 would be twice as bad as a 2. In this case, it's just where you landed in the decision tree. We're going to walk through each branch and each number in detailed. So first, we have definitions from the NASA Tech Note. Again, we've already defined handling qualities, but we're going to walk through these other definitions one by one so that we're clear when we use the chart, the flow chart, that we understand exactly what's going on. So first is the definition of compensation. It's the measure of additional pilot effort and attention required to maintain a given level of performance in the face of deficient vehicle characteristics. So it's more than normally required to perform the task. Anything beyond normal expected compensation would be a sign of a deficiency in the vehicle. So initially staying out of the flight control loop because of a concern over PIO is a form of compensation. So it can be mental compensation as well as physical. The role is defined as the function or purpose that defines the primary use of the aircraft. The mission is defined as the composite of pilot vehicle functions that must be performed to fulfill operational requirements. May be specified for a role, complete flight, flight phase, or flight subphase. And this should be clearly defined at the start of developmental or operational testing. The task is defined as the actual work assigned a pilot to be performed in completion of or as representative of a designated flight segment. Workload is defined as the integrated physical and mental effort required to perform a specified piloting task. How hard am I moving the controls to perform the flying task? How hard is it to do non-flying tasks while performing the flying task? There are many ways to measure physical workload, but very few to reliably measure mental workload. And we know that workload consists of effort required to both perform the task and compensate for handling qualities deficiencies. Next is the definition for performance. It's the precision of control with respect to aircraft movement that a pilot is able to achieve in performing a task. Pilot vehicle performance is a measure of handling performance. Pilot performance is a measure of the manner or efficiency with which a pilot moves the principal controls in performing a task. So in more common usage, it's the expectation for overall task performance that must be explicitly stated before we can use the Cooper-Harper scale and apply it properly. Scale uses decisions about attaining desired or adequate performance, so you have to know what's expected before you can actually do the rating. Though it was developed in 1969, the Cooper-Harper scale has withstood the test of time. It's been translated all over the world. You can see here the version used in Turkey, Russia, Japan, and even Israel. We'll now walk step by step through the Cooper-Harper scale. We see where the pilot enters the scale at the bottom and has to answer the first question. Is it controllable? Lack of controllability implies an inability to do the defined task within the defined limits. Answering yes means there is also a concern about retaining control in general. An ability to perform an alternate task doesn't make it controllable. It has to be the defined task. Assuming the aircraft is controllable, we then arrive at the next question. And really it's two questions. Is adequate performance attainable? Even if yes, is pilot workload tolerable? So it is possible to attain adequate performance with excessive pilot workload. And remember, we talked about workload being both physical and mental. The answer may be no, even if performance is adequate. If it is possible to attain desired performance with excessive pilot workload, there's probably something missing in the definition of the task itself. Always answer in the context of the task. Do not extrapolate unless you're asked to. So if the answer is no, then we know that deficiencies require improvement. Focus is on controllability, not aircraft characteristics. The aircraft has major deficiencies. A score of 7 indicates adequate performance, not reasonably attainable, but controllability is not in question. 8 and 9 are more fuzzy. Considerable compensation for control or intense compensation to retain control. In general, do not get too hung up between these ratings. Both indicate serious controllability issues. The aircraft really seemed uncontrollable, consider starting again with the is it controllable branch. If we answered yes to the previous two questions, we then land at the third branch. Is it satisfactory without improvement? So at least adequate performance and pilot workload is tolerable. There are deficiencies that should be fixed. This might be sufficient for a degraded mode operation where a single failure reduces task precision, but should not prevent the task from being performed. If the pilot answers no to this question, then we know that deficiencies warrant improvement. Perhaps the most confusing group of ratings on the scale is 4 through 6. They mix aircraft characteristics, performance, and pilot compensation. So we'll start at the bottom of a rating of 6. Adequate performance, but only with extensive pilot compensation. For 5, it's adequate performance with considerable compensation. So now we have to have the pilot discern what's considerable versus extensive. Hard to discern between the adjectives. We may be better to use aircraft characteristics of moderately or very as far as defining what objectionable deficiencies are. Now consider what a rating of 4 means. It means we've moved from adequate performance to actually desired performance with only moderate pilot compensation. So that's kind of a big change to go up to 4 from 5. Again, we went desired to adequate performance and moderate to considerable compensation. This is really the only conflict in the entire scale between a 4 and a 5. In the end, you have to make up your mind. So pick one and move on. The difference is not that big. Taking this branch has already indicated that it's not satisfactory and that there really are deficiencies that warrant improvement, and we'll want to do a redesign to address those. If we answer yes at the third branch, it gets us to the top region of 1 through 3. There are many pilots who will say they never assign a rating of 1 because they believe it would imply that it's a perfect aircraft. And a perfect aircraft requires no pilot compensation for desired performance. There is no such aircraft. But this argument is short-sighted. Again, Cooper-Harper pilot ratings are always given in the context of the mission task and its performance requirements. So do not rate the overall aircraft. It is satisfactory for the mission task without improvement, and the aircraft characteristics are highly desirable, and pilot compensation, even if some is required, is not a factor for desired performance. A rating of 1 is entirely appropriate then. So how about ratings of 2 or 3? In the case of a rating of 2, subtle difference from a 1, as the only changes are in good characteristics from excellent, highly desirable, to good, negligible deficiencies. A rating of 3 means that pilot compensation changes from not a factor to just minimal. So that's sometimes hard to discern between 2 and 3, and that's okay. The big decision point has already occurred. The aircraft for the mission task just performed is satisfactory without improvement. There have been attempts at modifying or simplifying the Cooper-Harper scale, and they've ranged from the hilarious to the ridiculous. So these attempts have reinforced 2 very important lessons. 1, the scale is not perfect, but it's a lot easier to mess it up than to improve it. We have nothing better to use, so in general, resist any attempts to change it. We're kind of stuck with the Cooper-Harper scale. So again, you may ask, well, what wino came up with this scale? It turns out George Cooper, after his distinguished career as a test pilot, ended up becoming a winemaker and had his own estate, the Cooper-Harper Estate Vineyards, and he produces bottle of wines that, depending on the year, will have a different test pilot label and different aircraft featured. And so for 2014 and 2015, I showed you the bottle of wines that the Cooper-Harper Estate Vineyard produces. Just kind of a humorous take on a Cooper-Harper scale. In this case, it's the Cooper-Moorhouse wine rating scale. So can the wine be swallowed? Would you buy this wine? Would you pay any price? Again, a little bit of humor from the Cooper-Harper scale to the Cooper-Moorhouse wine rating scale. Here's a little more humor in a Cooper-Harper rating. We often look at test pilots as difficult creatures to work with who are highly opinionated, big egos, and so on. And so you can kind of see this funny Cooper-Harper scale for dummies based on what the pilot's feeling and ego is doing at the time. So again, we have to define what a good handling qualities task is or requires, and that involves a lot of things. It's got to be a piloted task, needs to be mission-oriented, repeatable test maneuvers. We need clearly defined performance standards and control strategies. Needs to be operationally significant. The task duration has to be long enough to separate any transients and residual motions. Right? If we make errors in this task definition, it's going to result in widely different handling quality ratings using the Cooper-Harper scale. So here's an example of a handling qualities task definition for a Cooper-Harper evaluation. It involves pitch and roll discrete tracking. So the objectives are to evaluate the handling qualities in a tight closed loop tracking task. We want to evaluate the field system and control sensitivity characteristics and identify if there's any bobble or PIO tendencies. So our description is aggressively track the displayed signal and attempt to keep errors within the specified tolerances. So in paragraph C and D, we defined what desired performance is, and then we also define what adequate performance is. In the case of desired, it's keeping the target within plus or minus 10 mils in pitch for 50% of the time, and keeping the target in plus or minus 10 mils in roll for 50% of the time. So it has a measurable as far as what mil, and then it also is quantifiable in terms of the duration of time that it's within the desired mils. For adequate performance, you expect that to be loosened up a bit, and so it is. So adequate performance is defined as plus or minus 20 mils in pitch for 50% of the time, or plus or minus 20 mils in roll for half the time. So the performance requirements are clearly defined in this example. So since most engineers aren't necessarily familiar with what a mil and a target on a HUD and all that stuff looks like, here you see here the command bar. That's driven by the pitch and roll attitude errors that we saw on the previous chart. So the pilot flies to command the bar within the fixed reticle. So the pilot then would move the controls to center that command bar into the display on the bottom. And there you can see what a 10 mil circle looks like, and that's where desired performance is defined. And then you see what the 20 mil circle looks like. So it's going to be harder to keep the command bar within the 10 mil circle than it would be the 20 mil circle. And then again, remember, we have a quantifiable time-based duration that we can measure by reviewing the head-up display video after the task is complete. So we did this project when I was a student at the Air Force Test Pilot School in the late 90s. We performed it on the variable stability NT-33 aircraft shown there, and it involved 3 test pilots. We flew 9 sorties for 12.8 hours, and we looked at pitch rate limiting on the actuators for the elevator. We were able to do that through software, and we had different tasks, different models, and we'll look at some of these very short samples here from our representative runs to give you an idea of how this type of handling qualities task plays out inside the cockpit environment. So next you'll see some data. Here we have an aircraft with good handling qualities, and the elevator rate limit was a bit low, 20 degrees per second, but the aircraft in general was a good modeled transfer function aircraft. And the pilot flying this is Captain Roberto Cabbiati from the Italian Air Force. And for this run, he gave a handling qualities or Cooper-Harper rating of 2. And although we haven't talked about PIO ratings, he gave a PIO rating for this run of 2 as well. Both those are suitable, satisfactory performance, and that's a good flying airplane. So here's the video of what a run using a tracking task in a head-up display looks like.
We're on conditions.
Okay.
Here we are. You ready?
Ready.
Here we go.
Okay.
745 Alpha, traffic, no factor.
This aircraft
Contact
appears to be sluggish
32.5, 32.5.
in the steady state response. The initial response is pretty quick. All right. Up to this moment, the gross acquisition and fine tracking are both good.
2 miles eastbound.
I had no problems in keeping the target inside the inner circle. Initial response is good, and the steady state response is good as well. Let's see what happens during big pulls.
Cobra 63 traffic.
No problem. The aircraft
10 miles. Opposite
is
direction.
predictable.
T33, 9,700.
Mesh the roll.
So here you were able to see how the commanded target moved in pitch and roll, and how the pilot was able to track that target and keep it within the 10 or 20 mil circle. And we could quantify just by looking at this video after the fact to see if indeed it was within the 10 or 20 mil circle for 50% of the time. Next, I'll look at the same pilot who looked at an unstable bare airframe aircraft, so a bad transfer function, but with the same 20 degree per second elevator rate limit. And you can see that in this case, the pilot assigned a Cooper-Harper rating of 10, so it wasn't even controllable, and a PIO rating of 6, which is the worst on that scale. And you can see the PIO happening in terms of the data with, we'll see a rate limit turns up in a sawtooth kind of a plot when you see the elevator rate being on the limit. So here's what that run looked like.
The test right now.
Contact approach 126.5.
Aircraft appears
if they don't hear you,
to have a little bit of oscillations. The initial response is quick. The steady state response is a little bit slower than the initial one. Overall is a little bit sluggish, with a couple of overshoots over the target.
12 o'clock, 2 miles, left to right, flight level 200.
Gross fine tracking looks pretty good. The target is steady right now.
At 8 o'clock and 3 miles.
Stick forces are light to moderate in the 10 pounds range. Now there is a big pull. Oops, Oopla. And it departed.
So you can see the airplane departed, got into this pilot-induced oscillation. I also want to point out that, you know, airspeed didn't really change more than 5 or 10 knots, and the altitude stayed within a couple hundred feet during this entire tracking task. So just to give you an idea, you may have thought that by tracking that target, the airplane's speed and altitude would have been all over the map, and in this case, it was really not much of an issue in terms of speed and altitude. And so the pilot was able to assess the dynamics and the handling qualities of the aircraft just by flying this simple HUD tracking task. So here's another example of a definition of a handling qualities task that you would use and assign a Cooper-Harper rating. In this case, it's a ground attack. So your objectives would be to evaluate the ability to accurately perform air-to-ground diving deliveries, expose short-term longitudinal lateral handling qualities deficiencies if there are any, evaluate any longitudinal lateral PIO tendencies. So that's the objectives. And I don't have an example of this one in terms of video, but I just wanted to show you guys in terms of how you can define these with established criteria, that you maintain the dive angle within 2 degrees, you maintain the airspeed within 25 knots, and you have this fairly detailed defined performance envelope and task. And so you can see desired performance would be to track the array within 5 mils and no overshoots. Adequate performance is track the array within 7 mils and no more than 1 overshoot. So this was a ground attack handling qualities task that was defined, and the reference is shown there with Dave Mitchell and Dave Clyde and others. So for the third example, I'm going to use an example that involves a precision offset landing, and this is something you can relate to any airline or transport aircraft. So I know the first ones implied a military kind of weapons delivery, like air-to-air tracking or air-to-ground weapons delivery. But in this case, this is just a good old-fashioned, the airplane needs to land, but it came in on, say, instrument conditions and ended up slightly offset from the runway, and it needs to offset its flight path to line up with the runway and still land in a desired touchdown point, right? We can't have aircraft that are landing too far down the runway to make a stop, or that land short of the runway. So we want the airplane to touch down in the desired landing zone, but we're going to start the airplane from an offset condition that simulates, again, that the airplane broke out of the weather and happened to be a little bit misaligned with the runway, and then has to jog over to align itself with the runway before touchdown. So here's a video that shows a large aircraft and how that would look. So you can see sometimes the pilot was not even able to land. They had to abandon the task, so they weren't able to get even adequate performance. You also see how by coupling the lateral, directional, and longitudinal with the offset requires definitely a pilot involved in a closed loop task, multi-axis task that would require a certain amount of workload to accomplish that. So MIL Standard 1797 has many suggested handling qualities evaluation tasks. You saw some of the offset landings. We saw air-to-air, air-to-ground tracking examples, but you can also see close formation, aero refueling, many other different handling qualities task evaluations. So next we'll look at PIO as a separate standalone topic here. And PIO has a lot of different definitions: pilot-induced oscillation, pilot in the loop oscillations. Sometimes it's referred to as aircraft pilot coupling. That's what's preferred by the National Transportation Safety Board, and that's basically just trying to absolve the pilot of any fault. The airplane gets out of the phase with the pilot. But anyway, let's look at PIO as a topic by itself. Here's some definitions that we see from the MIL Standard 1797. PIO is sustained or uncontrollable oscillations resulting from efforts of the pilot to control the aircraft. The NRC Committee Report on Aviation Safety and Pilot Control defines it as rare, unexpected, and unintended excursions in aircraft attitude and flight path caused by anomalous interactions between the aircraft and the pilot. Dave Mitchell and Roger Ho used the definition: when the airplane attitude, angular rate, normal acceleration, or other quantity derived from these states is approximately 180 degrees out of phase with the pilot's control inputs. So here's a brief list of some of the causes of PIO, from simple to complicated. And there's different factors and there's different categories, whether it's a linear effect or a nonlinear effect. And here's the typical causes. You can see things that we've just studied as far as modes and motion in terms of short period. Roll damping, Dutch roll can be the causes. And then what to watch out for is shown here on the right. In the case of nonlinearities, it would be, so a lot of times you'll get a nonlinearity from a mode switch, or like we saw in terms of an actuator or software rate limit is a nonlinear effect as far as the cause. And you can see what to watch out for different pilots to be concerned with. So why do we pay special attention for PIO? I mean, it's been around for over 100 years. I think, and most people think, that even the first flight that the Wright brothers did had a PIO. We know early glider designs were susceptible to PIO as well. So meeting a flying quality specification can reduce the susceptibility. I mean, basic response requirements minimize risk. The control fuel requirements reduce chances of PIO. And most MIL Standard 1797 criteria, they don't explicitly address PIO, but they do reduce its susceptibility by satisfying the paragraphs for other stability and control items. And what we see is about every 15 years or so, there'll be a newsworthy event where a PIO occurs, and that's why it deserves special attention. We saw, obviously, the X-15, T-38, and F-4 had incidents in the 1960s. The YF-16 space shuttle in the 70s. In the 1990s, the F-22, the Gripen, C-17, and an MD-11 had an issue. And we saw F-35, and who knows what we'll find with the KCX and other aircraft that are currently under flight test. So next we'll go through some examples of what a PIO looks like.
We're too little, Cougar. We're too little, Cougar.
Give me some power. Some more power. Power, 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 damn it.
So there's a Hollywood example. Next we'll go to the YF-22.
The Air Force is still looking into the weekend plane crash that destroyed Lockheed's experimental Advanced Tactical Fighter. The video we're going to show you here was just released. It shows the pilot of the YF-22 desperately trying to regain control of this craft in a practice landing at Edwards Air Force Base. But the plane was too close to the ground. It finally slammed into the main runway, burst into flames, and skidded 1,000 feet. We're glad to tell you the pilot got out with only minor injuries, but this crash comes just as Congress is about to start reviewing the $95 billion YF-22 program.
And next we'll look at one from a little time ago, the F-8. So this video also showed, especially with the last view, of the offset landing task and how you can paint a desired and adequate touchdown point on the runway for this type of test. So the pilot had a distinct place where they were trying to land the airplane from an offset initial approach, and then it was on the go where the pilot got into the PIO. So as an aerospace engineer, you're always going to do the build-up approach. You're going to do the design, you know, from the equations of motion and the structures and flight controls and block diagrams and transfer functions, all that thing, the math models and so on that you'll do on the computer. Build the prototype, and then you're going to actually go to ground test before you would ever go into flight. And so ground test involves, again, things you would do to verify your simulation results, and flight control verification and validation, also in terms of redundancy management. But you can do taxi tests, all kinds of things on the ground that will exercise many of those modes and verify things are ready before you would go anything into flight. But eventually you're going to have to go to flight test, and you would always start with a first flight profile where you would look at some certain failure states, but you'd get through the first flight. Eventually you would expand the envelope and then get into high angle of attack testing. And then the last thing you do are these types of handling qualities tests where you require the pilot to get into the control loop pretty aggressively for some tasks to expose if there's any handling qualities cliffs out there or any tendencies for pilot-induced oscillation. Right? We wouldn't want to have that type of event that you just saw in the last couple of videos happen on a routine basis for the average pilot. So that's kind of the way the build-up approach works, from design to ground test to flight test, and then in terms of handling qualities at the very top of that pyramid. So in summary, this module covered flying qualities, handling qualities, and PIO. And the difference between flying qualities and handling qualities is handling qualities brings in the pilot's ability to perform the task for the air vehicle's role. And then near the end there, we saw that that PIO tendency of unsustainable oscillations or uncontrollable oscillations that result from the pilot and the aircraft get out of phase. So this concludes the module on flying and handling qualities.